Hello, my name is Doug Moss, and I'm majoring in mechanical engineering.
My name is Ben Stelter, and I'm an electrical engineer.
I'm Abdullah Wasmi. I majored in industrial engineering.
Hi, my name is Caleb, and I'm an electrical engineer.
Hi, my name is Kurt Nationalis, and I'm an electrical engineer.
Hello, my name is Adam Scora. I'm a mechanical engineer with the University of Arizona, and this is our Design Day video presentation. So to start off with, I'd like to introduce the problem that this team is trying to tackle. Police departments around the world, when they have an area that they wish to surveil, will often deploy a police helicopter to the area of interest. The problem with police helicopters is that they're incredibly expensive, they're very noisy, and, most importantly, they put a pilot's life in danger. Drones would be an alternative, however the problem with drones is that they have a very limited range and you would often need a drone operator only a couple hundred yards from the area of interest. To tackle this problem, this team has developed a relay system so that a drone operator can control a drone from several miles away. Our high-level requirements are that the drone has to be able to be launched from at least 2 miles away, the drone from the launch point has to be able to be flown for at least 200 yards, and will maintain a live video feed back to the operator. Finally, and most importantly, the entire system must be EAR 99 compliant.
Here, we have the concept of operations that shows the functionality of the best solution we developed through our work with General Dynamics. Now, the primary focus of this project was to develop a relay that serves as a communication hub for the system. This system starts with the user around 10 kilometers away from the launch point using a host computer which is logged into Wi-Fi at the site and running the remote screen sharing app TeamViewer on the Raspberry Pi desktop. The computer acts as the controller, which will be sending drone control inputs to the relay and from the relay to the drone. The relay is grounded and stationary with a connected Ethernet cable at the drone's launch point. The relay also connects to the drone's Wi-Fi with a Wi-Fi signal booster that allows for a 200-yard flight radius between the relay and the drone. Next, we look at the system block diagram, which gives us the in-depth look of the Shred system as a whole. Now we see, starting with the user going into the controller, which is being used in the remote screen sharing device, which is then connected through Wi-Fi. These controls are then sent to the relay, and at the relay, the Raspberry Pi processes those commands and sends it to the drone.
The final design of the Shred relay system consists of a Raspberry Pi running an Android emulator, downloading and using that drone's flight app, and controlling our choosing drone, the Ryze Tello. The main benefit behind this design is that as long as a user is able to remotely access the Raspberry Pi, they are theoretically able to fly the drone from any location as long as it has Wi-Fi. While building the Shred system, incremental tests had to be made in order to ensure that it was working. First, we had to install Lineage OS onto the Raspberry Pi. This connection was tested, and with Lineage OS, we were able to install the drone controller, which was needed to actually fly the chosen drone, the Ryze Tello. Next thing we tested was the actual ability to fly the Ryze Tello with the Raspberry Pi. As you can see, we were able to connect and fly the drone with the Raspberry Pi. The final and most important step, connecting to the Raspberry Pi via remote desktop and using it to fly the drone, was unable to be achieved. This is because of the Raspberry Pi's lack of ability to have both a simultaneous Wi-Fi and Ethernet connection, meaning that we can either connect to the Pi remotely via AirDroid, which we have tested, or fly the drone, which has also been tested, but not both. As soon as both connections try to happen, we lose connection to the drone and it stays stationary.
So now we can briefly talk about our testing results segment, and even though we don't have a complete project as a whole, we can talk about individual testing we've done for the drone, relay, and controller subsystems. So we're going to first take a look at the requirements given by General Dynamics mission systems, and then we'll break it down to the more specific requirements we've put in our SRVM. So first off, we were supposed to make a relay system. That's ultimately where we failed. That was the main requirement. But we do have a controller interface for both the Mavic drone as well as the Tello drone. Live video is able to be passed to both the drones in this project. Signal frequencies and power levels are staying within federal and state regulations, as you can see from this screenshot here. The Mavic is able to fly 200 yards from the relay And the Tello could with the additional booster. However, that's not the drone we would ultimately choose to use. The 2-mile requirement is essentially the one that we have failed to complete. With the Tello, we will sacrifice the 2-mile ability with our remote sharing, with the ability of actually being able to fly the drone. Both drones have a video-capable optic mounted to them already, so that is no concern. And as we said earlier, the controller interface is given a live stream video from the drone. So we're going to have to briefly talk about our SRVM here, which will include data that we've gathered from the Mavic 2, as well as specs from its datasheet. The GPS data is given on the map with where the drone is located, and it's able to land within a 3 feet accuracy of its home point, so it has really good GPS tracking. The drone subsystem does have a camera that records 4K 30 FPS video, and then that is sent back to the controller. The flight controls, that's given with the controller on the Mavic. You have a up, down, left, right. You can control the camera as well. Finally, the EAR requirement is that the Mavic Air 2 and the Tello and the Raspberry Pi 3 all meet EAR 99 and can be used for this project.
When looking at drones for the Shred project, we analyzed several drones along 3 main trade factors: performance, video transmission, and cost. These 3 main factors encompassed all the system requirements that our drone needed to meet. In the first drone trade study, we found the DJI Mavic Air 2 was our best option. We purchased this drone and began testing on it, but found that a design change to the project was needed. With our first design change, we had to do a new drone trade study, adding in some new trade factors, and found the DJI Mavic Pro was the best option moving forward. This drone was never purchased, however, as we found that our design for the project needed to change again. With our third design and our third drone trade study, we found the Tello Quadcopter to be our best option for integration into the project. However, this drone proved to be unable to be integrated into our project design. As such, the DJI Mavic Air 2 is the best option for this project moving forward, as it meets the most system requirements out of any drone that was analyzed.
This team has learned a significant amount about systems integration over the course of the semester. The first major thing that we learned about systems integration as a whole is that systems integration is extremely precarious when you involve multiple operating systems. We had a lot of clashes between different software packages that we were using because they couldn't communicate with each other or they worked on different operating systems. In retrospect, we should have started with the operating system and picked the software packages that work with whatever operating system we chose. The second major thing that we learned is that oftentimes it can be better to develop your own software package. Late in the semester, we found out that DJI has a developing toolkit for their DJI SDK, and if we had used that, we could have solved a ton of the problems that we encountered because we could have developed an app specifically for whichever operating system we used instead of having to rely on external data packages.
This concludes our video. Thank you very much for listening.